kiddos. Welcome back, and let's do a little review for Exam 6 this year, which is a veritable potpourri of chemical concepts. We've had several short chapters that we've put together in this one unit. We have some colligative properties, we have some thermochemistry, we have some rate law, and just a little bit of nuclear chemistry to do. So we're going to try to cover those topics in a couple of videos to review for this exam. So of course, let's begin with colligative properties. And if you recall, colligative properties depend upon the number of particles in a solution, not the type. And there are four colligative properties we talked about: vapor pressure lowering, freezing point depression, boiling point elevation, and osmotic pressure. Now, other than the definition for osmotic pressure, don't worry too much about that. I won't put any problems relating to osmotic pressure on your test. However, you should be aware of vapor pressure lowering, freezing point depression, and boiling point elevation. Let me just remind you of something. If I had a 10% or a mole fraction of 0.1 of a sugar solution, let's make it C6H12O6, glucose, and I used a different sugar solution, let's make it 10% or a mole fraction of 0.1 of sucrose, C12H22O11. It would end up that the vapor pressure lowering and the freezing point depression and the boiling point elevation and the osmotic pressure changes would all be the same, because it depends upon the number of particles, not the type. So whether it was glucose or sucrose, it wouldn't make a difference. Now, we did throw a little wrench in the works here. We talked about the Van Hoff factor, and if we had something like a salt like NaCl, that splits up into 2 particles per mole of compound. So we had the Van Hoff factor equal to 2 for something like that. So that would double the effect for something like NaCl. If I had used CaCl2, that splits up into calcium ions and 2 chloride ions. So the Van Hoff factor would be 3 in that particular case. So that would triple the effect. Once again, because it depends upon the number of particles, not the type. And in this case, we have ions that act as my particles. In the case above here, we had molecules that don't ionize or dissociate when placed in water. Okay? What I thought I would do is just review a boiling point elevation and a freezing point depression problem for you, and then I'll let you, on your own time, investigate vapor pressure lowering from your notes. So let's say I have an 87.5 gram sample of glucose, and I dissolve it in 500 grams of water. I want to find out what the new boiling point of my water would be, water solution, and the new freezing point. So the change in the freezing point is equal to the freezing point constant times the molality. The change in the boiling point is equal to the boiling point constant times the molality. So you'll see we have to find the molality to do both of these problems. And as you recall, I hope, molality is moles of solute divided by kilograms of solvent, which is oftentimes water. So let's go ahead and find the molality first. We have 87.5 grams of C6H12O6, and we'll need to convert that to moles. So I'll hop out of grams of C6H12O6 and get into moles of C6H12O6. And 1 mole of glucose would be the weight of 6 carbons, 12 hydrogens, and 6 oxygens. And I did that earlier. That's 180.18 grams per mole. So now I have moles of solute. And we'll divide that by kilograms of water. So we have 500 grams, so that'd be 0.5000 kilograms of my solvent. So let's see what the molality is here. We have 87.5 divided by 180.18 divided by 0.5000, and we get a molality of 0.971. Alrighty, so now we can find our boiling point elevation. So the boiling point elevation will be equal to the molality times the boiling point constant. So my molality is 0.971 molal. We just calculated that, kiddos. And the boiling point constant is 0.512 degrees Celsius per molal. So 0.971 times 0.512 gives me a boiling point elevation of 0.497 degrees Celsius. So since water's boiling point at sea level is 100.000 degrees Celsius by definition, my new boiling point will be a bit higher, 100.497 degrees Celsius. Let's do the same thing for freezing point depression. The freezing point depression is equal to the molality times the KFP. So 0.971, molality hasn't changed, and the freezing point constant for water is 1.86 degrees Celsius per molal. So 0.971 times 1.86 degrees Celsius per molal gives me a freezing point depression of 1.81 degrees Celsius. So the normal freezing point of water is 0.00, so my new freezing point would be negative 1.81 degrees Celsius. Now don't forget, if we're using a salt solution, we have to integrate into this equation the Van Hoff factor. So we have to consider I. So the equation would be delta T, let's do it for freezing point, equals KFP times the molality times I. And so once again, if it were NaCl, we would take the number 2, let's get a different color here to show that, for I, or if it were CaCl2, we would take the number 3, and so on. And we did a lab related to that, if you remember, when we were doing boiling point elevation. Okay? All right, let's move on, do a little thermochemistry now. And I have a table for you on your review sheet of some standard heats of formation. And remember, heat of formation is defined as the quantity of heat released or consumed when 1 mole of a compound, so it could be any of these compounds here, kiddos, is formed from its elements. And that's called heat of formation. Now we can use those to find the heat of a reaction using something called Hess's law. And so when we do Hess's law, as you remember, we add up the heats of formation of my products and subtract that from the heats of formation of my reactants, and that will give us the heat of the reaction. So remember, we have products on the left and reactants on the right. So for example, number 10, we have 2 carbon dioxides. So we have 2 times the heat of formation of carbon dioxide, which is negative 393.51 plus the heat of formation of N2. Now you'll notice N2 is not on this chart anywhere to be found. That's because it's in its elemental state, and the heat of formation of an element is 0. Now on my reactant side, I have 2 COs and 2 NOs. So I'm going to subtract out the sum of the heat of formation of those reactants. So 2 times the heat of formation of CO would be 2 times a negative 110.53 plus 2 times the heat of formation of NO, which is a positive 90.25. Okay, so let's do some math here. Let's add up the sum of my product's heat of formation. So we have 2 times a negative 393.51, and we end up with 787.0, and that's a negative 787.0. We're just going to go to the nearest tenth, folks. That's good enough for me today. Minus the sum of the heat of formations of my reactants. So that's 2 times a negative 110.53 plus 2 times 90.25. and I get negative 40.56. So we'll take a negative 787.0 minus a negative 40.56. Looks like we end up with negative 746.4 kilojoules per mole of reaction. Now remember that negative sign, kiddos, means that that reaction is exothermic, and the heat for that reaction would be placed on the product side of the equation. All right? Number 11, why don't you try number 11 on your own? So pause the video and see if you do it properly by coming back to the video and checking your work with mine. Okay? See you in a sec. All right, good. Did you put the products on the left-hand side and subtract out the reactants on the right-hand side? So 2 Al2O3s, so 2 times the heat of formation of aluminum oxide, which is negative 1675.7, plus 3 times the heat of formation of manganese, which is 0, it's an element, minus my reactants, 4 times the heat of formation of elemental aluminum, which is 0, plus 3 times the heat of formation of MnO2, which is negative 420.03. So let's see what we get here, kiddos. 2 times a negative 1675.7 gives me negative 3351.4. So negative 3351.4. That's on my product side, kiddos, minus 3 times a negative 420.03, and that would be a negative 1260.09. Negative 1260.09. So the heat of that reaction would be the negative 3351.4 minus the negative 1260.09, and we end up with a negative 2091.3 kilojoules per mole of reaction. And that, once again, is exothermic. The sign of delta H for that reaction is negative. Okay? Rather than doing another example like that, I want to do an example using the formal use of Hess's law. So this is not on your review sheet. This is a problem that I have for you over here. I want to find the heat of this reaction right here. And I'm going to give you 3 other reactions that we can use to add together to equal this reaction here. And according to Hess's law, if you can add the reactions together, you can add their heats together to find the heat of the reaction you're looking for. So let's change colors here. Go to blue here. If you remember, we start by drawing a line on these problems. And underneath that line, you write the reaction down that you're after. So we're after this reaction here. We have carbon graphite. That's elemental carbon, kiddos. Plus 2 H2s and a half of an O2 gas. So plus 2 H2 and a half of an O2 gas. And that reacts to form CH3OH, methanol. Now, if you look at this, I'm forming 1 mole of a compound from its elements. So this is really the heat of formation of methanol. That's what I'm after. Now, I'm just not going to look it up in a table. What I want to do is I want to use these 3 equations and their respective heats added together to give me the equation that I'm after. So the way that we do that is we look at the equation we're after. I want graphite on the left, hydrogen gas on the left, oxygen gas on the left, and of course methanol on the right. In my first equation, I have methanol, but it's on the wrong side. It's on the left side. So I want to put it on the right side. So I'm going to take this equation and write it backwards. I'm going to put methanol on the right-hand side. So that's CH3OH plus 3 halves of an O2. And then my CO2 and water I'm going to put on the other side. CO2 plus 2 H2Os on the left-hand side. Now when I do that, I have to change the sign of that the heat of that reaction to a positive 726.4. So I successfully have my methanol on the right-hand side, which is, of course, right where I want it. Let's take a look at the second equation. I have carbon graphite on the left-hand side, and I want carbon graphite on the left-hand side. So I'm not going to mess with the second equation. I'm going to write it down again just as it's written up above. Carbon graphite plus O2 makes CO2. That happens to be the heat of formation of carbon dioxide. And that's negative 393.5. Don't change the sign because we didn't have to turn that equation around. All right, now I need to get H2 on the left-hand side, and my third equation has H2 on the left-hand side. So I'm not going to turn that around either. I'm going to write it exactly as it's written. H2 plus a half of an O2 makes H2O. That's the heat of formation of liquid water. And that's negative 285.8. Now there's a small problem here. Let's change colors quickly. Do you notice I need two H2s? And I've only got one here. So what I need to do is double this reaction to give me two hydrogens. And when I do that, I have to double the heat of that reaction. Now, if I've done everything correctly, when I add these three equations together, I should get the one that I'm after. And if I do, I can add my heats together, and I can get the heat of that reaction. So let's change colors again, and let's cancel out things that are the same on both sides of the equation. You can help me. Looks like I have two waters here and two waters there that cancel. They're on opposite sides of the arrows. What else can I get rid of? Let's see. Looks like I have a carbon dioxide here and a carbon dioxide there. Those cancel. And I have 1.5 oxygens here. Now this gets a little bit tricky. I have one oxygen there, and then I have two halves. So I can get rid of a half of an oxygen here, not all of them. So I'm going to still have a half of an O2 remaining. Now if I've done that right, when I add these together, I should end up with the equation underneath my line. So I have CH3OH, which is what I need on the right-hand side. I have graphite remaining on the left-hand side. I have two hydrogens remaining on the left-hand side, and I know that's hard to read, but I have a half of an oxygen remaining on the left-hand side. So these three equations do add up to give me the overall equation, so I should be able to add up their heats. So let's add these together and see what the heat of that reaction is. 726.4 plus a negative 393.5 plus, I'm going to use my parentheses key here, 2 times a negative 285.8. And I end up with negative 238.7 kilojoules per mole of methanol produced from its elements. Okay, now that's the formal use of Hess's law, and you're expected to be able to do a problem like that. Now I've done 5 or 6 others in your notes, so go back and review your notes in the videos on Hess's law if you're a bit confused. Okay? All right, now back to our review sheet. We're going to stop the first half of the review right now. When we come back, we're going to do a little bit more with thermochemistry, and we're going to look at some potential energy curves. So we'll see you soon. Bye-bye.